Okay, we're going to start today by introducing some new notation, and it's kind of notation of convenience, okay? Because for what we're going to be doing next, it will make things really useful. And it's not a question of right or wrong, it's just in certain contexts it's sometimes easier to write things a certain way. So I've got the following situation, right? I have an, dn, y, dxn, and then we'll do a couple of these. Plus a1 dy dx plus a0y equals, assume it's not zero. I'm going to introduce a similar notation to something you may have seen in Calc 1. In Calc 1, the d dx notation, some authors like using this notation. It means the exact same thing, the derivative with respect to x. I'm not a big fan, again, because there's no analogy in Calc 3. We don't have a partial derivative notation for that. But in this class, what we're going to do is we're actually going to drop the subscript. Because the idea is, if it's clear what the independent and dependent variable is, when you say take the derivative, that actually is not a good instruction. I mean, Calvin, take the derivative. With respect to what variable? Well, with respect to the only independent variable we're probably talking about at the moment. We're okay with that, right? Give me the antiderivative. With respect to what variable? Probably the only variable we're using. I can do that in Calc 1 and 2, not in Calc 3, right? Because now there's multiple potential independent variables. But in this class, we're only doing one independent variable. We are not doing partial derivatives or partial integration. So it actually makes sense if we're, right now, let's say we're using x and y. Then when I use big D instead of dx, it's the same implication. So the new notation that I want to introduce, not that you're going to go to this from now on, but it's an alternate form. And I've asked some questions like on the practice test. Some of you saw them and went, oh my God, what is he saying? an d to the n plus an minus 1 d to the n minus 1. Now, first I'm going to write the y, but then I'm going to show you something you're going to like. I can factor out the y. And then it becomes an d to the n plus an minus 1 d to the n minus 1, all the way down to a1d plus a0 applied to y. Because we could do that with any derivative notation.
If that notation is used as where the subscript is the dependent variable, then wouldn't this
Independent
be...
variable. Independent.
Oh, sorry, independent variable. Then wouldn't this be y dx?
No. This d, this capital D, is the exact same as this dx. That, by the way, did anyone use this notation in your Calc 1 or 2? Mm-hmm. You never use it? Okay. I've seen people use it. I don't think it's notation of convenience, because I don't think it saves us any time. But it's legal. These mean the exact same thing. These aren't the derivatives. These are the operators. These are the instructions to take the derivative. So in this form, I'm saying this of y, and so on, and so on, and so on. Okay? Now, we're obviously not going to go really high. We're probably going to stick with second order. But then I'm going to show you something. You're going to like this. Okay? Let's do a problem we've already done. I've got, let's say, something of the form, I don't know, 2 times the second derivative. And how about minus 5 times the first derivative, and then plus 3 times the function. And let's keep it simple. It equals 0 for now. So we know exactly how to do this problem. This one's easy. We find the auxiliary equation, and what's our auxiliary equation? Be
2m squared minus 5m plus 3.
Plus 3, and that would give us, or I'll do my part, 2m minus. Green one. Okay, so I get m equals 3/2 or positive 1, and we'd finish off the problem. You know how to do that. I'd like you now to apply this notation to that problem. If I apply this notation, it will now look like 2d squared minus 5d plus 3 all applied to y. You always do it that way. You don't put the y, n times. You can't. It's not wrong. If I didn't know any better, I'd say it almost looks like I could go like this to y equals 0. Now, this is an operator. This is not a value. But look at the form of my question and look at your auxiliary equation. See any vague similarities there? Do you see the auxiliary equation in the actual question itself now? Yeah, this is one of the reasons people actually like this notation. My auxiliary equation, I can just go straight from here. Oh, my m is going to be 3/2 and it's going to be positive 1. That's convenient. It's not necessary, but it's certainly convenient. Does it change any aspect of the problem or how I'm going to approach the problem? Not at all. But the notation allows me to do other things. You say, am I multiplying? No, I'm applying this to this. Don't we, when we first learn second derivative, don't we say we're actually doing, we're doing the derivative of y. So I'm kind of doing the same thing. I'm doing 2 times the derivative minus 3 applied to the derivative minus 1, all applied to y. Even though we don't think of this as really being a factoring thing, from this standpoint, it still gets me back to here where these are differential operators. Now, this is the sort of the lead up to what we're going to do today, because we're going to use this notation to solve some really icky problems. All right? There's 2 versions of this problem. The first we're going to look at today, and the second one we're going to look at near the end of the course. Those who had linear algebra, did you guys do any solving differential equations using eigenvalues and eigenvectors?
Yeah.
Yep. It's in the Larson book, it's 7.4. It's considered a pretty important application. It's not the only one, but it's a fairly important application. We are going to do that in our class near the end of the course, which is part of the reason we do it near the end is up until recently, you could take linear and diffie-q at the same time. And I often taught them both in the same semester. So I would push off the eigenvalue, eigenvector problems in this class as long as I could so that you'd see them in linear first. You don't want to learn it in this class any more than you want to learn your logarithms in chemistry or your derivatives in physics, right? You're going to use them there. You don't want to learn them there. This would be like learning your Spanish from me. That would probably be a bad idea. So because you can no longer do that first, it still makes sense to push it towards the end because it's near the end of the book. We're going to solve systems of differential equations of a very specific type at the end of the course. And it will look exactly like what you did in linear. Today we're going to do a very different form of the same thing. We're going to solve systems of differential equations, but not using eigenvalues and eigenvectors. Literally using just simple algebra. And it's going to seem kind of weird at first. So I'm going to give you an example. Okay? And I'm going to do it sort of more, I'm going to use x and t. Now, this is a problem. This problem right here is something we can do at the end of the course using eigenvalues and eigenvectors, and it's not even a complicated problem in that context. But I want to do it slightly differently. So x and y are both functions of t, which is kind of how most of our problems are going to look. We're not going to have 3. The eigenvalue eigenvector problem, I can give you as many as I want, as long as it produces a square matrix. In this class, we're only going to do 2, because it's too messy otherwise. Now, when you're looking at this, you're going, okay, I wouldn't even know how to start this. Well, I can use substitution and addition, right, to eliminate variables, but is it really going to eliminate anything? Or just make the left side more complicated? I don't really want to add the derivatives. That's probably not a good way to go. But what if I take both problems and rewrite it using the big D notation? Okay, how would I do that? Well, first of all, what if I rewrote it in such a way that let me see, keep it real simple. That first of all, I put everything on the same side. I'm going to rewrite it like this. Dx dt minus 4x minus 7y equals 0. And x plus dy dt plus 2y equals 0. Did I just write that correctly?
Negative x.
Did I?
Negative x.
That's what I'm asking. Does that look right? Make sure I just wrote that correctly. Now, let's do the D notation on the derivative parts. There's no y derivative in this statement, so there's no d for that guy. There's no x derivative in this statement. But I do have an x derivative here and a y derivative here. So here's the statement, same thing. Let's rewrite the first part. Could I write it like this? D minus 4 applied to x minus 7y is 0? What do you think?
Sure.
Yes, no, maybe? That's D applied to x minus 4 applied to x, so D minus 4 applied to x.
Just to make sure, you said that the D notation is with the independent variable in the front of the D, right? So, or
So in
the
this
subscript-
case, what's the independent variable in this
X.
case?
X.
T. I don't need to write of, that would be like saying big D, little t. That's not something that's in question. It's right there. X and Y are dependent variables. So like in the problem over here, Y is a dependent variable. I'm applying derivatives to the dependent variable. You can't apply the derivatives to the independent variable because then you just get 1. Yeah, so only to the dependents. Now, how would the second line look?
D
D plus 2
times y minus
Well,
x.
let's say how about negative x,
Negative x
plus D minus D plus 2
d plus 2
times
y.
applied to y. Now stare at that for a moment. Does it match the things? Have I actually done any math yet? No, I've restated the problem twice. Now, you have a younger brother or sister who's in 9th grade algebra or whatever. They're going to walk into class right now. They don't know this is differential equations. And you're going to say, I'd like you to solve this system of equations. Think of D as D could just be a number. How in the world could you solve this differential or this system of equations? Well, could I just use the addition method? Yeah. All right, let's say I wanted to eliminate the y's first. Well, what would you do? I want to eliminate the y's. So could I multiply this equation on both sides by 7 and do this equation on both sides by what? I didn't give myself much room.
D plus 2
D plus 2 and to both sides. And by the way, you don't, it's not on the other side. That, sometimes we get really, that's ooh yuck. D plus 2 is the operator. You can't go, I can't have function and then d dx. It doesn't work that way. Now, so if I put all this together, let's rewrite the top line. The top line now reads d plus 2, d minus 4 applied to x minus 7 d plus 2. And that 7 is just a coefficient. Applied to y, and it's still 0. We are going to do problems where there's a function on the other side, but for right now it's a 0. That makes life kind of nice. And then here I have negative 7x plus 7d plus 2 applied to y, and that equals 0. Okay, I know this is still true. If I gave you any equation and I said differentiate both sides of the equation, we know that's still true. If I gave you an equation and asked you to do an algebraic manipulation like multiplication or addition to both sides, we know it's still true. So I know these two equations still are true. How about if I add them together?
The 7s and D plus 2s and Y's cancel. And then you're
So here I'd have d plus 2, d minus 4 minus 7 all applied to x equals 0. Well, if this were algebra and not differential equations, could you multiply that out and say it's d squared minus 4d plus 2d minus 8 minus 7?
Sure.
If this were remedial algebra, and let's just call these x plus 2 times x minus 4 minus 7, it all equals 0. You couldn't solve that. You'd multiply it back out and refactor, wouldn't you? Everybody understand that? That's the only way you could do this.
Would you want us to make the statement that this is true only when x is equal to 0? Or do we just...
X is not 0. In fact, x can't ever be 0.
0.
X is a function of t.
Oh, it's... Yeah,
X
right,
is
it's a
never going to
function.
be 0.
Okay,
No.
thank you.
And d is not a variable, d is an operator. But what does this give us? Does this refactor?
All right. 5 and
I'll do my part. Heck, I'll go a step further.
3, 5.
yeah, and then it's plus 3 minus 4. Yeah.
if I were to expand this whole thing right now, it would look like, don't write this, I don't want you to do this in general, but if I were to expand this whole thing right now, it looks like this. Where were they, minus 2. That's what it would look like if I expanded it. And then I'd say, what's the auxiliary equation? And you would tell me, and it's what? M plus 3 times M minus 5. And then I'd say, what are the roots to my auxiliary equation? You'd say they are what?
Negative.
M equals negative 3 or 5. Therefore, give me two linearly independent solutions. Oops. X1,
E to the negative 3.
e to the negative 3
Oh,
T.
t,
yeah, T.
and x2,
Then 5T.
huh. And by the way, everything we've said is true and correct so far. We're not done. I don't know, we're close to halfway done. So now I could actually say then that how does that keep making it back into the fold? Okay. I can say that with certainty. Remember, we're trying to find x of t and y of t. We've just found x of t.
Are these still roots of the auxiliary, even though it's written in the?
Well, no, because if I said if I rewrote that using our formal notation,
Yeah.
then wouldn't our auxiliary equation be m squared minus 2m minus 15?
Right, and then we still get the same
Yeah.
independent solution.
So that's why I can literally read it from that. I don't actually have to go through all of this. That was what I was showing you. I can read. My auxiliary equation is going to look exactly the same as the differential equation, so m equals and m equals is still the same. Don't say d equals. D is not a quantity, D is an operator.
Okay.
But could you say, looking at this, that m is negative 3 and that m is 5?
Yes.
Yeah, without having to rewrite all this. That's what I wanted you to see. I can save myself a tremendous amount of time by, I said, I'm going to write this, I don't want you to write this. I want you to go right to here without having to redo it because it's sitting right there. Now, that's x. How did we find y? Oh, or excuse me, that's x. We got it by eliminating the y. Can I do the same thing now, eliminate the x? Yeah. If this were baby algebra, that's exactly what you'd do. So, hopefully I left myself enough room. Probably not. Zero back up there in a moment. So now I want to eliminate the x's. Excuse me. Well, I don't think I need to do anything to this one. What should I do to this one? How about
Multiplied by D.
d minus 4? Does everyone agree? Because of the minus sign. So, I'll finish over here. So when I rewrite that, where is it? It's over there. So I'd have d minus 4x minus 7y equals 0. And then the second line would read negative d minus 4x plus, d minus 4 d plus 2y, and that also equals 0. So now when I add these together, this is going to give me d minus 4 d plus 2 minus 7 all y equals 0. I'm getting this really weird sense of deja vu. Same thing, isn't it? Does everyone see that?
Yep.
Coincidence? Hardly. No, it has to be the same thing. It will always be the same thing. And that's a cause for rejoicing. So why did I have to do the whole thing to begin with? Because if these are not zeros, I have to do the whole thing on both sides or I will never be able to get, yeah. Because those were both zeros, I really didn't have to do it a second time. I already knew that was going to be the result. It's because I looked ahead. But most problems, these are not zeros. They're functions. So I have to do both sides because it's going to, when I do that d plus minus 4 to both sides, if that's not a 0, oh, I'm doing d minus 4 to a function. Does that make sense? That's why you still have to do it to both sides no matter what. Yeah.
So y1 in this case would be e negative 3t, and y2 would be e 5t.
Yeah, so hold that thought. So can I'm gonna cheat. can I say y1 equals e to the negative 3t? That's what John was asking. Can I say that now, do you think?
Yeah.
Yes. So therefore, is y of t the same answer? No. Most definitely not the same answer.
Because they're multiples, or?
Let's start with this. It would only be the same answer if C3 is equal to C1 and C4 was equal to C2, and that's probably not going to happen. Mathematically, it could happen, it's just not going to happen. So, we're most of the way done. We're not done yet.
But aren't the auxiliaries like multiples of one another, even though they're different equations? So wouldn't we have to do like x e to the whatever and then do that for the others?
No. Y is separate from x.
Okay.
If this were a perfect square, then I would have, one of them would be e, the other would be xe.
Okay.
For that variable. But x and y are completely unrelated to each other. They just happen to have the same auxiliary equation. So the question, Dushanti asked a good question. It appears that I'm doing repeats. No, but that's x, this is y. They're completely different. Now it's down to the constants. I can't have 4 constants. I can only have 2. Because think about it, whatever x is and whatever y is, when I go back there and I put everything together, right, it should work. How am I going to figure that out? This is actually the easy part. Okay, let's take those solutions and substitute them in the differential equation, and we're going to be able to figure out how the constants relate. Some of you may remember doing this with the eigenvalue, eigenvector problems. You've got different constants, but I might have C1, it might be something like this. This is C1 plus C2, but this one ends up being 5C1 and minus 3C2. I'm still going to see C1 and C2, but I maybe see a multiple of it. Well, why don't I just call that a different? No, because I want to see exactly how those coefficients are related. C1 can be any real number, but if this was 3C1, that means this coefficient is always exactly 3 times this one. Yes, it's different, but it's always different exactly as a multiple. That's what we're going to figure out. What multiples are we going to get? So, let's see. I'm going to take this one because I can't see my original equations. They're way too far away. So, what is dx dt?
4x plus 7y.
All right, so based on that, what is dx dt? So let's actually differentiate, in other words. It's going to be negative 3c1 e to the negative 3t plus 5c2 e to the 5t. And what must it equal? It must equal the right side. And so what's the right side? It's 4x you with me? And then, what was it? Plus 7y? Plus. So far, so good? I didn't do anything. Well, I did take the derivative. dx dt, because that's x of t, this is dx dt. And the right side is 4x's and 7y's. Now, let's put these together. On the left side, what are the coefficients of e to the negative 3t? It's just negative 3c1. What is it on the right side?
4c1.
You with me on that?
Okay.
Did I write that correctly?
Yeah, that's good.
Huh. If I throw that over, won't that be negative 7c1 equals exactly 7c3? So what does that tell you about, if I decide to solve for c3, isn't that just going to be negative c1?
Yep.
Got one of them knocked off. Now let's look at the next one.
Oh.
On the left side, I have 5c2. What are the coefficients of e to the 5t on the right side? Well, it's going to be 4c2 plus 7c4. Is that right? So if I throw that guy over, I have c2 equals 7c4. You know what? I think it might be easier if I do this. Unless you want to do 1/7. I'm lazy. I don't want to do 1/7. So what I'm going to do is replace C2 with 7C4 and replace C1 with negative C3. I could go the other way, but then it'd be a 1/7, and nobody wants that, right? No, fractions, yuck.
I'm kind of remembering something we did in linear algebra where if we had constants that were, or coefficients that were equal to one another, therefore they would be like linearly dependent solutions of something, or...
It's just something different.
Okay.
Yeah, that's not about the coefficients, that's something else. But yeah, that would be the linearly independent functions. But so we're actually in a place where we can stop. That's the relationship between C2 and C4. Remember, they're both coefficients. That's the relationship between C1 and C3. In the effort to avoid giving a fractional coefficient, I'll go this way rather than C4 equals. So now I'm not going to restate y. Y stays the same. I'm going to restate x. And how am I going to restate my x? I'll restate it right here. C1 is now negative C3 e to the negative 3t. And C2 is now 7C4. So C4 can be any real number and it will solve this problem. C3 can be any real number and it'll solve this problem. But once I've selected C3 and C4, now the coefficients for x are set in stone. Does that make sense? That's why we don't call them two different things. Because whatever this is, this has to be exactly the same thing negative. Whatever this is, this has to be exactly 7 times bigger. We've now completely finished this problem.
You know how you move the negative so you could go with 3 and 4 instead
Yeah.
of 1 and 2? Couldn't you go with 1 and 4 if you wanted?
No.
Or 2 and 3?
No, 1 and either go with 1 and 2 or go with 3 and 4.
Why is that?
Because you're saying I'm going to use one set of solutions or the other set of solutions. Sometimes these come with initial conditions too. It actually just, it gets a little bit too convoluted if I do it that way. Because again, the original problem, the way it's, you're going to go one or the other. It's just easier. Now, we did the simplest version that could possibly be done. If we did this using eigenvalues and eigenvectors, it was probably a little less work. I just had to find the eigenvalues and eigenvectors for a 2x2, diagonalize it. Probably not that terrible. I would have eigenvalues. Can anybody tell me what the eigenvalues would have been, by the way? Just see if you remember. My eigenvalues would have probably been, I don't know, something like -3 and +5.
That's what
They would have shown up right there.
Yeah.
We are going to do this problem again at the end of the course from a different point of view. So why did we do it this way? Because this allows us to solve other types of problems. In linear algebra, we can do this problem here. We can't do this problem here. I just threw in a function of t for fun. This is impossible in linear algebra.
A function of 2 with respect
To have anything that's not an x or a y. To have a, now what we're going to do is throw in functions of t and see how that affects it. In other words, not 0. This is the only way to solve that problem. The linear algebra version solves any number of equations, but they all have to be linear equations, and when everything's to the same side, technically homogeneous. No functions of t. Oh, okay. So in other words, the linear algebra approach, as valid as it is looking at a very different type of situation with a lot more restrictions. We're going to not have any restrictions, except we're only going to do 2 equations. Not that we can't. Do you really want to do this with 3 equations in 3? The elimination part is just, it's so time consuming. It's so long and drawn out. I don't want to do that. Okay. What did I say last day? This is one of the more tedious topics. Remember me saying that? It's just, this was the simplest problem you're ever going to see. It's not going to get simpler than this one. And it still took us that much work. Now we're going to add a layer of complication to it.
It's only 3 boards.
What's that?
It's only 3 boards.
There's no part of this process that I want to be difficult, but there's a lot going on here, okay? Similar problem, not the same problem. Actually, I think I just did the same problem. Oh, you know what it is? Sorry. Similar problem, not the same problem, because we're going to add something now. I shouldn't have erased everything, sorry. 4x plus 7y plus e to the 4t Now, the functions that I'm adding, huge restriction. What do you think the restriction is going to be?
Can't be negative.
4 things. What did I just added e to the 4t and t.
Yeah, you added functions of t, so we can't do it the other way.
It has to be a function of your dependent
Well, yeah,
variable.
it's got to be a function. Yeah, it's got to be t's. It can't be like q or something. No, I mean, what did I just add? I added an exponential and a polynomial-ish.
Yeah.
Are there any other things I could have added?
Sines,
No,
cos-
so
Sines and cosines, anything else?
Logarithms.
No.
They're exponential.
The big 4. I can't do this problem if I'm doing tangent or log or secant. Because of the nature of the problem and the way we're attacking it, we can't do it if it's something else. Part of it is I need my derivatives to still kind of look like the original functions, and only sines, cosines, e's, and polynomials and more or less look like their own derivatives, right? Log doesn't, right? Tangent doesn't, and so on. That doesn't get you off the hook. It just means there's not a bazillion types of problems I can solve, but I have a system of differential equations, fairly low level here, but that just got way more complicated all of a sudden. Okay? So, I can't really shorten this, so let's rewrite it like we did before, but I'll kind of shorten it. So we had d minus 4x minus 7y, but that's equal to the function on the other side. Negative x plus d plus 2y equals negative t. Did I capture that correctly? Because I erased a lot of it, I know. I think I did that. Let's see. So now what we did before, we're going to get rid of the y's first. So we're going to do the whole d plus 2 to both sides. So I need to kind of rewrite the right side in a moment. I'm going to go d plus 2. And by the way, because we already did the other problem, I'm not going to do all of it over again. I'm going to fast forward to the results we already know. But we don't know what the right side is yet. So this is now going to be, I'm going to rewrite this as d plus 2 applied to e to the 4t. Okay? Down here, we're going to multiply by 7, so that makes it kind of easy. Can I just put a 7 in front of here? Yeah, that's not an operator, that's a coefficient. Okay, look at my new thing. We already know what the left side is going to be, because we've already done the left side. So this is where I'm saying, I'm going to fast forward. You don't generally get this opportunity, because you're not doing the same problem twice ever. I just did the homogeneous version, so we already knew what the general solution looked like. So I'm not going to redo all of this, it's not necessary. So what is the left side when I add these? Won't it be d plus 3,
D minus 5.
d minus 5
X.
applied to x? But what's the right side?
D.
Ooh.
So that's derivative 4.
So I'm going to apply the derivative to this. What will that give me?
4 e to the
4 e to the 4t. Then 2 of these. And now,
Minus t, 17.
whoa, that is a little different, isn't it? Okay, it's a lot different. Left side is the same. Can I say that my homogeneous solution is the c1 e to the negative 3t plus c2 e to the 5t? But now there's a particular solution. Okay, we'll get to that one in a bit. I do have to do the same thing again for the y, because I've got to apply these, operators to both sides. I think I can erase all this. So in the first case, the whole problem was a homogeneous. So we don't actually separate and say, okay, we have an XH and a YH. But now we do know we have 2 different pieces. And we found the first one easier of the 2. So now when I do the second one, Okay, now we want to get rid of the x's, so we agreed that we're gonna do d minus 4 to this row, correct? We're not gonna do anything to the top, we don't need to. So the top is still e to the 4t, but this one is now, sorry, my equals should still be blue. Oh, what am I thinking here? All right. D minus 4 applied to negative t. Everybody follow this? So I already know the left side, excuse me, I know the left side once again. It's not really in question. So when I combine all this, we already did this once. D plus 3, D minus 5, Y, but the right side is now what? So D applied to that would be negative 1 plus 4t. Beautiful. So, like before, I'll give different coefficients because now that might change. I mean, we're pretending like we're doing this for the first time. That's what I'm saying. Okay. So far, so good? Sure, got everything there. Okay. Now let's do the x. Where is x? Oh, right. Let's do the x first. Yeah.
Will this be kind of like undetermined coefficients where we have like a homogeneous and a
Kind of
particular
like.
and add them to each other?
Kind of like.
Or is this exactly
Exactly
undetermined?
like.
Okay, okay.
Why? Don't look at this as you have two separate problems. I want to solve this problem. Where did this come from? What was this? We factored something. So this was d squared minus 2d minus 15 applied to y, correct? Oh, so when I use the method of undetermined coefficients, I'm just going to stick them right back in there and do, this is exactly what you already did. This
So
is not different at all.
Our general solution will have two homogeneous plus two
Well,
particulars added.
Think of it as x and y. Keep x and y mentally separate for the moment.
Oh, okay.
For the moment, keep them separate. Okay? So when I'm doing this, but when I do the undetermined coefficients, this is a part of the game. Right? So let's do the x. I think I can get this in there. I hate erasing as I go, but. Okay, so we're going to do the x first. So method of undetermined coefficients in the x, what do I want to call my xp? Well, let's see. That's, right now, that's 6e to the 4t, correct? I haven't added them together. So it's going to be something with an e to the 4t. And then what's the other term going to be?
Minus B7.
Well, that's got a t in it. So shouldn't it have a t in it, or is it a t squared in it? Is it a t cubed in it? What's the highest degree that I should have for my t's?
1.
That one. Because if I have a higher degree, let's say I decide to use a t squared. Then when I do two derivatives in the function, I'm still going to have a t squared in my answer. It won't go anywhere. So t is going to be the highest thing I have. That's how you remember, oh, okay, I can't go higher than t because then I'll have something higher when I get done with my derivatives. So what do I want to call it? bt plus c. I got to have everything in descending order. And by the way, it is highly likely, probably the case, that c is not going to be 0. Oh. So I don't want to just start off by assuming it's 0. Can I have a c that's not 0? Yeah. Because when I differentiate things, things combine. Now, what is dx dp? dt? That would be 4a e to the 4t plus b. And the second derivative would be 16a e to the 4t, and that's it. Now what do we want to do with those? Stick them back in, set them equal to this, and then we figure out our coefficients. We've done this before. We've not done it from this point of view, but what I'm doing now we have done. You guys turned in a quiz on this, everybody got everything right. It was, you know, we're not worried about repeated solutions right now, right? We're not worried about weird complex solutions. This is pretty straightforward. So when I substitute these back in, there's my second derivative. Then I want -2 times my first derivative. Then I want -15 times y, or xp. Okay, and what is all this supposed to equal?
4e
4e
to the 4t.
plus, well, 6e
It's
to the
all supposed to equal 6e to the 4t.
minus 17.
No, it's minus 17.
Minus
Okay, see that
17.
far. All right, let's clean up the left side. So I have 16 of them,
-8.
-8 plus 15, what's that? Minus 7 of them?
Wait, it was -8 and -15.
Yeah. I think it was like adding the negatives together.
Oh, gotcha.
16, -8, -15? Or I'm sorry, -15, I think that's right. Oh, yeah, that's right. I think. I need you guys to correct me if it's not. Do I have any t terms left?
That seems about right.
So minus 15 bt, and do I have any constant terms?
Oh yeah,
Minus
15c.
and 2b.
So plus -2b minus 15c.
Yeah.
And now we're going to equate coefficients. So first off, what does -7a equal?
6.
6. So a equals -6/7. Next, what does -15b equal?
Negative 7.
That equals -7. So b equals positive 7/15. And then finally, what does -2b minus 15c equal?
Plus 0 or 0?
0.
Yeah.
But b is not 0, therefore c is not going to be 0 either, is it? Oh, so I have -2 times 7/15 equals 15c. So -14/15 equals 15c. So therefore c equals -14/225.
Of course.
Kind of yucky. Are we done with this part here?
No. We're never done.
Are we done with x of t in other words?
Oh yes, x of t is done. Oh wait, no.
Got
The
everyone
general
there?
solution for x of t is the particular plus the homogeneous, no? So
Yeah, so I said, I'm pretending like we haven't done this problem before.
Oh.
You already know that the C1 and the C2 we're gonna change to match those guys. We're doing this problem as if we're doing it for the first time. I wanna make sure everybody understands that.
Okay.
We fast forwarded to get to here because we already knew what it was gonna be, but if we hadn't done this problem before, we would still have to address these guys as a separate entity. And then we would find the same thing we did before. We were gonna call C1 -C3, and we were gonna call C2 7C4. That's piece of cake, that's easy. But right now, we're very specifically solving the non-homogeneous part. So we can now say, right over here. I don't want to erase it again. So our x of t now, we know is going to be of the form, I think we said -c3 e to the -3t plus 7c4 e to the 5t. Then what?
Whatever.
I got my coefficients, where are they? A was, help me out.
-6.
-6/7 e to the 4t.
B is 7/15.
And then it was, I lost where it was, where is it?
B equals
7/15 t. I got, everything's written in black, that's my mistake. I'm having a hard time finding it. And then the constant term was
-14. Oh, it's -14/15.
negative.
And then it's, oh, and then.
Is that all correct?
Actually, it's positive and then
Did I
sine
copy it
15.
badly?
It's 15 times, -15 times c.
So that's what?
Oh yeah, -15 times -c is
Yeah.
just a positive net 14.
Yeah.
which-
You have -2b minus 15c.
Yeah.
Negative.
No, c's gotta be negative,
But
because you moved it to the other side.
-2b equals.
No, that's correct, it's negative,
Okay.
negative
Oh, that's
14.
negative, yeah.
Yeah, that's negative. Okay, are we done with x of t?
okay.
Yikes, that was a lot of work, wasn't it? That wasn't a that wasn't a short, sweet process, but it was a correct process.
Can you go back and explain like how you got A's 6, 7?
Oh.
Like what about the 6?
Okay, let's go back to here. Sorry, let's go back to here. This is 6 e to the 4t minus 7t. I'm not doing that, I'm doing that problem. Okay? So my method of undetermined coefficients, I need an e to the 4t and I need a polynomial of degree 1 and descending. Okay, so now I took my two derivatives, I stuck them back into this. Second derivative minus 2 times first minus 15. And then when I did that, that gave me the left side of this equation, which I then set equal to the right side, which was that. And then that's the undetermined coefficients. And so we got negative 7a has to equal 6.
Why? What about the 7? The 7t.
E to the 4t, I'm only looking at e to the 4t.
You're just matching up. It's like
Yeah,
it's
equating, I'm
similar.
equating coefficients right there.
Okay.
Now let's go for the t. Negative 15b has to equal negative 7.
Mm.
And now let's go for the constant term, which has to equal 0. And that's what
Oh, okay. Okay.
Yeah, is there any part of this process that's difficult? No, it's all bookkeeping, but it's really long and tedious. I warned you guys, you know. I said to you guys, this isn't my favorite problem just because it seems to take, this is not even a complicated one. This is low level, and we're only halfway done.
Oh, that's true.
Now, the fact that we'd already solved the homogeneous earlier, you know, that's kind of cheating. But if we hadn't, we would do the homogeneous first, independently of this part. Because we always got to get the homogeneous solutions first. Then we would have done this. Well, why would I do the homogeneous first and not it all together? What if? What if that was one of those? Now I got a repeated solution. Does that change everything?
Yep.
Yeah, and it makes it a lot more icky. You all agree? We've done this problem already, or a version of that problem.
Is it also better to solve for the homogeneous so that we can pair up the coefficients like
Yeah,
there? So that-
but it doesn't matter if I do that earlier or I do that late, because again, I do the homogeneous independent of the particular.
Okay.
I do not even consider the particular when I'm doing the homogeneous and vice versa. But what if I got a repeated solution? By the way, I mean, I did throw an e to the 4t, you know, which is kind of in between negative 3 and 5. You know, I could have messed up and put an e to the 5t there. That changes everything if I got a repeated solution. So that's why I'm a big fan of get the homogeneous out of the way, and that's another safeguard. In case I did have a repeated solution, that would definitely change that right there, wouldn't it? Okay.
If you have a repeated solution like you were saying, would you put that extra x in front of the?
Well, in this case, t. No, if let's say I did have a repeated solution, then that would be a t.
Okay, it'd be in front of the particular, not the homogeneous.
Only a particular. Well, no. Okay, these guys were not repeated, but I'm saying, what if one of these was this guy?
Mm.
What if both of these were repeated? Well, then I already put the t in here. And then you had a quiz problem where these were repeated and it showed up there. Then you'd have a t squared in your particular.
Okay.
That we've done that problem, so we have an idea how to attack it. We didn't love it because it meant, oh gosh, I have to use a product rule. Oh, I know it was pretty taxing. I know. I think pretty much everybody did it right, by the way. So now let's do.
The y.
Where are we in the problem?
We have to do the y now.
Yeah, have I got the y?
No, we did the x particular, now we have to do the y particular.
Don't I have it somewhere up here?
Well, we
Right
have,
here?
that's the y homogeneous.
Yeah.
But that's what we're going to use here.
Yeah, that's
Oh,
what-
okay,
yeah,
okay.
yeah.
I get- I don't have to start over. So now I can erase all of this, correct? Because I've got it up there. None of what was particular for x, none of that will have anything to do with what's particular for y, because you don't have the same stuff going on. Now, the homogeneous parts look the same, but not the particular parts. So all of this is going,
The trash.
what do they call that, fire sale? Right? Everything's going. All right. So what do we got for the y? We got that. So what is my y particular going to be? Well, you want to use new letters? You're doing this as a completely separate problem. Within the X, I can't reuse A, B, or C. That would be really confusing. Now I'm doing Y, it's a completely separate problem. You can reuse anything you want at this point. So if you want to go A, B, C, that's not an issue. Within the same problem, you can't use the same symbol multiple times. Like if you're doing an integration, you've got second derivative, you're going to first, I'm going to call my arbitrary constant C, and then the next time I do it, I'm going to call it C again. They kind of have to be different C's because they're in the same answer at the same time. But these are two completely separate answers. So I have no problem with saying A e to the 4t.
Wouldn't it be the same, just plus BT
It does look like it'll be the same, doesn't it?
plus C?
Because I probably put it in that order. That's just interesting, isn't it? I probably shouldn't have erased everything, huh? By the way, this is coincidental that we got the same thing. That's not a guarantee. Kind of lucky, but by the way, are we going to get the same A, B, and C? Do you think?
No.
No, probably quite different.
Yeah.
Because I'm also
Yeah, we have a different equation we're
Yeah.
gonna.
yeah, it should be the same. So. Oh, I keep erasing the things I probably should have left up here. It's happened more than once. All right, so let's put everything in. Okay, so I've got 16a e to the 4t minus 2 of these, so minus 8a e to the 4t minus 2 b's, and then minus 15 of those.
Where are we plugging
Did
it
I
into
mess that
again?
up, or is that right?
Into
I'm sorry, where are we-
Where are we plugging it into again? Like which one?
Oh! I kind of wrote it small. If
Okay.
I expand that it was second derivative minus 2 times first derivative,
Yeah.
I can't put it here. That won't be of any use.
Yeah.
That's so careful. You're not going to take this derivative plus 3, multiply by this derivative plus minus 5, and then, no, because those are differential operators. We can't treat those as coefficients in that sense. So this is what we got.
Just,
Did I
next
miss
to the-
something?
Next to the minus 15b, we need a t.
Yes, you are correct. I need a t. And what does all of this equal?
E to
E to
the
the
4t
4t
plus
minus
4t minus 1.
E to the 4t plus 4t minus 1, which is different from we got in with the x's, so we know our coefficients are different this time. So on the left side, once again, when we add them up, it was negative 7a e to the 4t, negative 15bt plus negative 2b minus 15c. All right, so I have negative 7a equals 1, don't I? Because that's the coefficient there. So a is negative 1/7. Next, I have negative 15b equals 4. So b is negative 4/15. And finally, I have,
Negative b
Negative b
minus
minus
15c.
that should be 2b, shouldn't it? That
Yes.
should be 2b. Negative 2b minus 15c equals negative 1. So that would be 8/15 plus 1 equals 15c. How about if I do that? Just rearrange it a bit.
Sure.
So I just stuck this in there, little flip-flopping. So that would be 23/15 equals 15c. So c is 23 over 225. So hopefully I didn't mess that up. I think that's what I got the first time. So now over here. Negative 1/7. Negative 4/15. And then 23. Yikes. All right, if I wanted utter certainty, absolute assurance that this is correct, what would you do?
Right.
You'd take the derivative of each of those and
Shove
then
them
stick
back.
them on the other side and blah, 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 blah. Thing is, we've already checked the homogeneous. So could I just do the particular at that point?
Sure.
Yeah. Is it necessary? Not really, because that's what you kind of just did here. That's how you found your particular. But it would be an independent way of finding it. So if I said I got for the top one, and by the way, this is another reason why I need these both to be C3s. When I take 4x's and add it to 7y's, if I have 4 different coefficients, C1, 2, 3, and 4, nothing combines, does it? Oh, but if I'm using C3 and C4 in both cases with different coefficients, then I can combine them, I can cancel them, and things will work out nicely. That's why I have to get it down to 2 and not 4. Again, nothing would work nicely. Wow. And I just said this is considered a lower level problem. Well, wait, what would a higher level problem be?
Partial derivatives.
With
Sine and cosine.
non-exponentials and logarithms.
Second derivative?
No.
No.
How would that affect it?
I'm good.
So I'd have d squareds?
Have cubics.
Then I might be, yeah, everybody understand that, I could easily make that a higher degree. I'm not interested in that problem. I'm interested in this process.
Where the higher degree may give you like you'd have to use Euler's probably at some point.
No,
Like you
if
get, like,
it's a higher degree,
negative.
you very likely are gonna have a third degree polynomial. You got a factor, which we know that's hit and miss. So let me check something out here. I'm pretty sure. No, the author's pretty, no, he does. Problem 7. Problem 7 and 8. He does second order. He does second order, and then we do this entire process, which means that it's highly likely you might have to factor a cubic. I'm gonna avoid that problem like the plague. Because again, you can't do the differential equations if you can't get past the algebra step of factoring. That's why I just don't need to go past second degree unless we get lucky and you have a third degree polynomial but no constant term. Then we know it's a fairly simple factorization. But I don't want to rely on that, okay? Let's do another one. It's not about the answer, it's about the process, as you guys know. So, textbook here. No, by the way, there are initial value problems. Yeah, is it?
Just to go back, to be clear, the very first step, finding homogeneous of both x and y and comparing arbitrary constants.
Right.
Before you touch yp.
Yes,
the part.
but isn't that what we did before anyway? I mean, isn't that what we've done on any non-homogeneous equation? We've solved the homogeneous first. I just want you to get used to that. You'd prefer to stop at the homogeneous. But we realize, oh, the homogeneous solution has nothing to do with the other one. The homogeneous solution, when I plug it in, gives me all zeros. That's why I have to include it, because the particular is very specific. If I left off the homogeneous completely, this would solve the problem I just erased. This would solve it. But that would mean there's exactly one solution. No, there's infinitely many. Because every version of this, every combination of coefficients added to this will solve it. Now, what if I give you an initial condition, these c's are not 0? Oh, this will not solve the initial condition part. Okay. It does seem kind of odd that the homogeneous doesn't even affect the stuff on the right side. You're right. The homogeneous only gets 0. But what it means is, like any parameterized solution in linear algebra, you got a specific solution, and then an infinite number of things when added to that gives you the same solution. So that's why I got to include all of those guys as well.
So then, to that problem that we were doing, to get these two general solutions for the specific
Right.
functions,
DE.
right? What is the general solution to the ODE then? If you're just getting two generals.
Well, you're getting, this is the general solution because you're solving two different functions simultaneously.
Oh, so
this is a
that
system of equations.
so
The two together is the
two together, not meaning you're adding them, but just two separate like
right. So
functions.
let's. I don't care if we finish so much as let's get at least another one started. Hold on, let me grab it.
I'm skipping.
It's not too bad.
You got this, you got this.
Just erase the f(x) equals 0.
Oh, here we go. Here we go.
Separable.
Like these are good answer.
It's all separable.
All separable?
Yeah, that's very simple.
Just not the
these two separate problems, or are they just the same?
No, this is my system of equations.
Oh, I see.
No, they're not separate problems. All right, so what we'd like to do, and you notice it's already been grouped in such a way that you don't have to rewrite it. The first one we had to rearrange, right, to make it homogeneous or to make stuff on the other side. You notice on the right side of the equals are all my t's. On the left side is everything x and y-ish. All right, so let's go right to the big D notation, right off the bat. What do I got here?
2 big D minus 5 in parentheses x
Okay.
plus big dy.
Plus big dy, beautiful. I want that to be absolutely automatic, you don't even have to think about it. That's gotta be an easy step. But it's not gonna be an easy step unless you do a few problems. Right, you gotta kinda get the hang of the language here. Everybody okay with that?
Yeah.
These are my extras, this is derivative function. So this is 2 times the derivative of x minus 5 times the function itself. Next line?
D minus 1x.
Plus
is that a
dy.
plus dy.
Equals 5 e to the t. Okay, doesn't matter what order you do it. What do you want to get rid of first?
The dy.
Because
You want to get rid of the y's? Okay. This is the part that should feel like remedial algebra to you. If this were baby algebra and I just had x's and y's, you'd say, okay, just add the right coefficients. The d's are not coefficients, but in this sense, treat them like they are. Okay, they're operators, but if I do the, let's see, I want to get rid of the y's, so what do you want to do the top by?
-1.
So you want to do the top by -1 or the bottom by -1?
Bottom by
Bottom by
-1.
negative 1.
Probably the.
Oh, actually,
Or the top
probably
one.
the top
Probably the
one,
top
because
one.
you have to.
So then you get a positive coefficient? I like
Yeah.
that. I think that's actually sound strategy. I always look for the easiest way. If you guys haven't figured that out by now.
It doesn't matter though, right?
Nope, nope. But when it comes right down to it, it's not even about right or wrong or even about ease, but when you're solving something later down the system, having a positive coefficient versus a negative just takes away one possible error there. Did some of us make a negative sign error over here? Yeah. Even at this level, we still can make that kind of mistake. So when I add these, I get what? Be careful.
Negative D.
I get negative 2d
Oh, right. Plus.
plus 5 plus
D.
d minus 1. Did I do that right?
Yeah.
I'm doing the negative, hold on, make sure I got that correct.
That's correct.
That's correct.
Negative 2d plus, okay,
Yeah.
In terms of x.
equals
4 e to the t. So it's negative d minus
Negative d plus 4.
equals 4. Right.
do you like the way that reads?
Yeah.
Beautiful.
Could I do it like this?
No.
Would that be okay?
Yeah.
Yeah.
Might it be easier to interpret if I did that?
Yes.
Yeah.
You don't have to, but I think it might, for a lot of us, might be a little easier to interpret that. I don't think we made him say, let me make sure I wrote that problem down correctly. Yeah, okay. Can you tell me what is the auxiliary equation here?
M minus.
It's just m minus 4, correct?
Oh.
Yeah.
Oh, it's because it's first order. That's why.
Do you agree? It's just m
Yes.
minus 4?
Mhm.
So what's my m?
4.
4
So what's my x1?
e to the.
E to the 4t. So far, so good? That's a 1, sir. Now let's do the y's. So, or I should say, let's get rid of the x's. Sorry. So I'm going to get rid of the x's. So what am I going to multiply the top one by? I need to redo this. Sorry. I'm going to be clever here. Leave myself some space. All right. We're now going to get rid of the x's. So if I do the top one by, let's say, d minus 1, then what am I doing the bottom one by?
Negative.
Well, it has to be negative, yeah.
The negative of, one of them's got to be negative. Doesn't matter which one I do,
Where,
right?
can't you just, oh, never mind.
And I actually do have to physically perform the whole thing. The very first problem I did was a homogeneous problem. I didn't really need to do this twice as I should because we're gonna get the same answers, but I have to do this twice because of what it's gonna do to the right side. Right, it does change everything. So, when all is said and done and there's nothing left to say or do, the x's will cancel, right? And what am I gonna get in the y case? I'm gonna get d minus 1 dy equals. That's right, right? I'm not even gonna bother doing that because those are gonna cancel.
Yeah.
I'm being really lazy right now. What's the right side gonna be?
Oh, e to the t minus e. Whoa.
What?
Whoa.
That's cool.
Calm down there, bro.
Yo. Chill.
Can we say that?
Sure.
I think we can say that.
Why not?
And then what's the
Bombs.
Wait, don't you have to multiply by the d?
d minus
You
1
did.
d?
You differentiate. Right?
The derivative of e to the t minus e to the
When
t.
you add them up, it's just like d
Right?
squared. D squared minus.
Everybody's okay with the zero then?
Yeah.
Okay,
Yeah.
no question on the zero.
Yeah.
Now, let's do the second row, those are gonna cancel, and then I have the negative of 2d minus, it is minus 5, right? Yeah, negative
Yeah.
of 2d minus 5, where are we, dy. Oof, careful here. There's a 5 there, you put the negative 5 if you want. So what are two derivatives of that gonna look like? It's just e to the t, right?
E to the t,
So I have negative 2 times 5, so wouldn't that be negative 10 e to the t?
Yeah.
Yeah.
Now, I just want negative 5 of them. Negative, negative,
20.
positive. Does that look okay?
Yeah.
Big D just means take the derivative, but it is e to the t. That made this kind of friendly. So that's 15 e to the t. Now what about this? Well, I should multiply it all out, right? Or should I? Well, no, I'm adding those two together, aren't I?
Yep.
So when I add them together, what am I going to get?
Yeah, it's negative.
That plus that. So how about if I write it as d minus 1 minus 2d plus 5 all dy. Can I do that?
Yes.
Some of you are nodding, some of you are shaking.
Question. So when you did the two derivatives of e to the t,
The two derivatives. No, I didn't do two derivatives.
it was
2 times
two
the
times
derivative.
the first derivative, right?
Right, but it still is a t.
5. Yeah, gotcha.
If it helps you, maybe rewrite this as negative 10d plus 25. Would that help if I wrote it like that? Negative 10 derivatives, which is still e to the t, plus 25 e to the t's, and that's what I have here anyway. Just as long as we get that. Now, this is the negative of d minus 4 dy.
M minus 4. M equals 9. What?
Equals
Oh, no.
15 e to the t.
Well, we're doing the homogeneous part first.
Right.
Yes, yes, yes. Excuse me, equals 15 e to the t, that's correct. But I want to do the homogeneous.
Oh, wait.
So what's my m?
Yeah, 4 and 0.
Oh, that's true.
What is the solution?
Yeah.
This presents kind of a quandary, doesn't it? That will be addressed in a moment. So what does it, did I write?
So special.
Okay, so it looks like we have two linearly independent solutions over here. What's one of them? E to the 4t.
Wait a minute, that's not
Well,
right.
what's the second one? I'm sorry, y. Y1.
E to the 0.
So
1.
1.
Whoa.
Huh. Huh. Presents sort of a quandary. I don't think we lost anything over here, do we? I don't think there's anything there. We have d minus 1 and we have that. And when you take those guys and add them together, I think that's exactly what we got. So when we did that to those guys, we got, it looks like we got a second one. Now, when we're doing all of this, let's not worry about the homogeneous part right now, because we already know it's going to be a linear combination. We're gonna finish that process. Okay. And we also be able to calculate the coefficient in front of the 1, which could actually end up being what? 0. Give me a little wink there. Now, how do I do the particular part?
We have
Well,
to-
that actually, in this case, is really not that bad, is it?
It's just E.
Because what is the differential equation in the x sense that I'm actually solving?
D minus 4.
That's pretty low, isn't it? It's first order. That is not gonna give me that much trouble, is it? Okay, and what am I doing in the y case? Okay, well, I'm doing an extra d minus 4d. So it's second derivative minus 4 times first derivative. Well, we would want to multiply that out. Like before, might it be prudent for me to take the negative and put it on the other side?
Yes.
I think it would be very wise. I'm gonna go like this. So now it's second derivative minus 4 times first derivative. So I'm actually gonna need to take 2 derivatives for the y. I only have to take 1 derivative for the x. Okay, I don't believe we have any repeated solutions.
Is
that
so
correct?
is it because that's y1? It's not a repeated solution because aren't they both to the 4t?
Oh, I'm sorry, you just lost me.
So x1 is e to the 4t over there.
Right, but remember,
it's
x and
because
y are
they're
unrelated.
different, so it's not.
No,
repeated.
it's only repeated if I got
it's-
4 with multiplicity. Let's make sure everybody understands that. Why? Because I'm writing these as 2 separate answers, completely. You're differentiating x independently of the y, and then you're throwing them all together. Yeah, it's a valid question, but it's only within the same function that I'm gonna get multiplicity. And I just don't think you're gonna see many of those. Not that you can't, they're just less likely. So, let's do, where is it? So, what is my particular solution for x? Just a e to the t, okay? And then dx dt, boy, that's gonna be tricky. Yeah, okay, I think it's the same thing. So now, what does this actually say? It says first derivative minus 4 times function. That's what that says. So if I take first derivative minus 4 times function, and what's that supposed to equal? It's just whatever the right side is, agreed?
Yeah.
So negative 3a e to the t equals negative 4 e to the t. So a is what?
4/3.
4/3. Wow, that was not even that interesting, was it? So right now, it looks like we've got I'll put it up here. It looks like our x of t is just c1 e to the 4t plus 4/3 e to the t. Not too bad, right? The y is going to feel very similar for obvious reasons, except the y I do actually need to have 2 derivatives. So, y is separate so I can reuse the a if I choose to. But again, the y equation also has an e to the t. But in the y case, this is second derivative minus 4 times first derivative. So I do have to take 2 derivatives. So, yp is a e to the t. So then the first derivative obviously is a e to the t. And then the second derivative is, of course, a e to the t. Didn't really get all that complicated, did it? So what am I going to do now? I'm going to take the second derivative, and then what? Minus 4 times the first derivative. And then that's all supposed to equal, again, are you getting that overwhelming sense of deja vu? Or is it vujade? You've never done any of this before thing. The left side looked exactly the same in both cases. Is that a shock? Wasn't that what happened with the last time we did it? Didn't the left side, when I did everything, didn't the left side produce exactly the same equation? It was the stuff on the right that wasn't the same, because the coefficients were not the same. So therefore, a equals 5. So it appears, unless we made a mistake somewhere, and I don't think we did, it appears that y of t is so far. C2 e to the 4t plus c, we'll call it C3, plus 5 e to the t. Okay. It wouldn't have mattered at what point of the problem we did this. We might as well do it now. We have to determine now the relationship between the homogeneous coefficients.
Between both functions.
The C1 on the left and the C2 and C3 on the right. We have to determine that relationship. So what are we going to do? We're going to ignore the particular and then just go back and throw it in. And here's the cool thing. By the way, I kind of didn't mention this. When I did it in the very, very, very first problem, I only put them in the first equation, do you remember? And then I found the relationship between the two.
It'll always be the same.
If I had only done the second equation, I would have gotten exactly the same thing. It'll always be the same. You don't have to do both equations. Did everybody catch that? I took the derivative of dx dt, and then I said equal to this stuff, and we got the relationship between C1, C2, C3, and C4. If I had done the second equation, I will get exactly the same thing. Why? Because they had to work both simultaneously. Because that's what you just solved. Now, if I totally messed it up, it wouldn't work in both. But I think we would have noticed if we totally messed it up way before then. So when I'm doing this, I only need to put it in one of the two equations, and neither one of them looks terribly complicated, so it doesn't really matter which one I do. So, which one do you want to do?
The top one.
Let's just do the first one. Okay, let's make it easy on ourselves. Get rid of this stuff here. I think we're okay. I don't think we're going to lose anything. But you guys all wrote everything down anyway. Now, we're only looking at the homogeneous now. We're making the assumption that our particular is going to work because of the way we found it. Now, we could check the particular by taking derivatives again, and I would be really surprised if it didn't work, because I think we would have discovered any arithmetic error over there. So, what is dx dt?
4C1 e to the
I'm sorry, but we're not doing this. This is, sorry, xp, or excuse me, xh, sorry. And then what is dyh dt?
4C2
4 C2 e to the 4t, and that's it. Now, we're going to take those two derivatives and then those functions and stick them in here. So what do we get?